Mira, a ver si te funciona el
So we switch now to English, and I have the pleasure to present Roger Bello, who is assistant professor at the Department of Chemistry, and he's an expert in computational chemistry and electron dynamics in atoms and molecules. And this is the title of the talk. So he's going to talk about electron dynamics in atoms and molecules induced by attosecond pulses.
Thank you. I don't know about being an expert, but I'll do my best. Okay, so I'm going to talk about electron dynamics in atoms and molecules induced by attosecond pulses. No? Okay. So in photoionization, just describing just a little bit, it's a process that is very sensitive to electron correlation. That means that you have to include electron-electron interaction. No? In most cases, if you have, for instance, valence photoemission, in which you remove an electron from a valence shell, you can get away with using the Hartree-Fock approximation or including less to none electron correlation. Some cases that won't work, but anyway, we can put it aside. But then you can have core level photoemission or JDK, photoemission plus shake-up, in which you remove an electron from a molecular atom, and then you can promote one of the electrons from one orbital to the other. Okay. Then you can have or JDK plus shake-up and all possible combinations of all of these processes. No? So any comprehensive theoretical study of photoionization must include electron correlation. So I'm not going to explain, I'm not going to detail how this method works, but because I won't have time for that. But the idea is to take advantages of the methods that we have developed within our group during the recent years to study electron dynamics induced by attosecond and femtosecond pulses. Okay. So I'm going to be splitting my talk in two. First, I'm going to talk about mapping ultrafast dynamics of excited state in lithium hydride molecules. And then I'm going to talk about an atom, electronic coherency in argon through interfering one antiphoton ionization in the vicinity of phase-back resonances. So phase-back resonances are double excited states, basically. Okay, so let's start by the molecule first. Move on. So your run-of-the-mill pump-prof experiments, this is pretty basic, but I think it's important to explain, is that you have the molecule in neutral ground state, you come with a laser pulse as a pump, you excite the molecule to a neutral excited state, you let the wave packet propagate back and forth between the inner and outer turning points of the potential energy curve, and after some delay, you come with the prof and ionize the molecule. Okay, so usually what you measure is the momentum of all the ejected particles. If you have a cold trip, if you have a BMI, then you have to split it another experiment. But anyway, let's assume that you can measure the momentum of all the ejected particles. Okay, for that, what you need to calculate the initiation amplitudes. So from the excited state to the continuum. That is the methods that we have developed. And for the bound and neutral states, usually what we do is to use quantum chemistry packages. So mol Cas, mol Pro, or Gaussian. And then you have to put all together, so the time dependence Schrödinger equation, and see what you get. So we're going to use lithium hydride as a benchmark because it's simple enough that you can do it almost exactly. It's only for 4 electrons, you can put 4 of the electrons active in your active space. Okay? Briefly, I'm not going to spend too much time on this, but what we do is to expand our time-dependent wave functions in eigenstate of the Hamiltonian. This expansion will include the bound states of the molecule or an atom that are below the ionization threshold, the continuum states that depends on the cation, the state of the cation that you left behind, the angular momentum of the photoelectron, and obviously the energy of the photoelectron. Now, if you want to include nuclear motion, which is what you should do if possible, You also have to include the vibrational bound or dissociative states of the okay. Why this expansion? This expansion is very useful because at the end of the day, the coefficients provide direct access to the probability of being in these specific states. Let's say that you want the probabilities, you have to take the square of the coefficient. So you don't have to project your final wave function onto anything because the information is already encoded in the coefficients. Okay. So we have this expansion, we plug it in the time dependence Schrodinger equation, and what you get is a system of differential linear equations, which is pretty simple to solve once you have the Hamiltonian, no? So these blocks are just the coupling between bound states, bound continuum, and continuing in case that you need it, no? In case that your photon ionizes the molecule. Okay, so usually this matrix element has this shape in which you have the dipole couplings for each internuclear distance, average over the vibrational states that the initial and the final vibrational state. Okay, so what is the caveat of this? That you have to calculate the dipole couplings for each internuclear distance, which is the most expensive part of the calculation. Okay, so as again, we take lithium hydride as an example. For the neutral state, we use quantum chemistry. We do an MRCI with singles and doubles from this active space, which is pretty big only for electrons. We use normal triple zeta basis functions, and we put some additional Ripper functions to be able to describe this. To be able to describe the Ripper states. Okay. And for the continuum state, we do a CASI for the cation states using the orbitals of the neutral. You can choose the other kind of orbitals, but this is the best approximation. And we perform a cross coupling just to impose the correct boundary conditions on the scattering wave function. Okay. Well, so just to have an idea, so you have to calculate all the ionization probabilities at each internuclear distance, so at each of these points, no? And I'm going to show how this looks like for two electron energies, different electron energies, as a function of the internuclear distance. This is the dipole coupling, no? For each possible angular momentum of the ejected electron. So you have to calculate each one of these curves and just average it with the vibrational wave functions from the time dependent, so on and so forth. Okay. Well, the goal was to explore the dynamics on a excited state. So the obvious choice will be to get the A single sigma plus state. No, has a funny looking shape because it changes from ionic to covalent. That's why it looks that way. Okay, so we calculate first the time independent spectrum, absorption spectrum, which is just the square of the dipole couplings for all the bounds states, and then dissociative and the dissociative. So these are above the dissociative IP, and this is what we get. So we see that we can excite effectively the A state. We use 400 nanometer pulse with 5 femtoseconds, which is pretty broad. And then for ionizing, we use a 200 nanometer pulse, which is going to ionize effectively the molecule. Okay. So we do that on the time dependence Schrodinger equation for each time delay. So, and the first thing that we can calculate, or the more simple stuff that we can calculate is observable, is just the ionization, you know, the total, which is the red curve, and just the dissociative, you know. So one of the things that we can notice here is that most of the ionization is dissociative, and this is explained because if you notice the lithium hydride plus ground state only has it has a shallow minimum, no, it doesn't hold too many bounds vibrational state. So this is expected. And the only point where non-dissociative ionization is more likely to happen is around the outer turning point, no? Which is around 40 to 45 femtoseconds. No? All when the wave packet is all the way just right here. Okay. Other thing to notice is that it's symmetric with respect to the outer turning point, which is kind of expected. So when the wave packet moves all the way out and then comes back, it's expected to have the same dynamics when it's coming back. If nothing happens here, which is we don't have any non-adiabatic couplings or anything weird, so this is expected. Other thing to notice is that we have some kind of weird oscillations for very short and long time delays. No, so we zoom in and we can see the oscillations, and this has a very simple explanation. So if you plot the population on the excited state, so no ionization for each time delay, what you see is that you can recover the same oscillations just at short and long delays. Actually, what is happening is that if you perform the Fourier transform of this spectrum, you recover the energy difference between the excited states and the bound state of the molecule. So basically, what is happening, what it tells you is that you have some kind of rapid flopping between the excited state and the ground state. Okay, so the pump not only pump population to the excited state, but also can dump some of the population back to the ground state. So this is what kind of unexpected. A little bit more differential observable that you can look is the photoelectron energy. So that means that you measure the photoelectron. This regarding the energy of the fragments, no, the lithium plus hydrogen plus dissociating. And this is what you get, and you can do the other way around. You can measure the kinetic energy release disregarding the electron kinetic energy. So just measure the lithium plus hydrogen plus kinetic energy. This is what you get. Again, it's pretty symmetric with respect to the other turning point, which is what we saw in the last slide, and is kind of expected. But there are also other features that are very possible. No? So we notice that there is a minimum around 25 and 65 femtosecond delays, which is the wave packet is located around 6 atomic units at those times. We know that because we can actually plot the wave packet and follow the evolution in time. And what is happening is that if you plot the photoionization cross section, so all of these lines that I plot a few slides before, you sum or the square of all of these and plot as a function of the nuclear distance for several photoelectron energies, what you notice is that it has a minimum around 6 atomic units, which is where the wave packet is located at those time delays. And what we speculate is that actually this minimum is because of the changing of character of the potential energy curve, from ionic to covalent, and that's why it has this very huge minimum there. And this is obviously visible on the spectrum, no? Meaning that the whatever you measure is being filtered by the photoionization amplitudes, which is also kind of what you expect. There is also this kind of fork shape that the kinetic energy release has that is a little bit annoying, but also has a good explanation. So in order to explain this, what we try to do was we implement a simple model in which we replace the photoionization amplitudes here by just the Frank-Condon factors to see if it was an effect of the wave packet moving, or was it just a pure electronic states or what a characteristic of the scattering wave functions or something like that. No? So we did that just by using the Frank-Condon. We recover this weird shape, so we can say that this just is the pure wave packet effect. But still, the question lingers: why goes to zero? No, and it's the explanation is very simple. So what is happening is that the wave packet is moving out, stopping at the other turning point because it doesn't have enough energy to leak out or just to do something else. and stops and then goes back, and that's why it go to zero. No? And if you plot the mean value of the kinetic energy of the wave packet on the excited state, which is the pink curve, you can nicely reproduce the shape of the kinetic energy release that you actually measure. So what we can get of this, that the wave packet dynamics is being completely mapped onto the kinetic energy release of the fragments of your measurement. We can also look at the photoelectron angular distributions, since we have a very good description of the continuum. No? So for that, we pick 2 electron volts, which is at the center of the distribution, more or less. And we can plot the angular distributions for all of these delays. As you can see, the angular distribution changes drastically, but recovering the same shape for the full vibrational period. No? So the wave packet moves back, change angular distributions, then comes back, and you can recover the same shape. And this is also an effect of the potential energy curve changing character from ionic to covalent, that the angular distribution of the photoelectron change too much. Okay. So conclusion of this first part, the EMF paths reflects the change of character in the potential energy curve, which is at least I haven't found any other study that proves this kind of stuff. The dynamics of the neutral state is completely mapped on ionization yields as long as you're using correlated methods. The kinetic energy release obviously map the wave packet dynamics, filtered for ionization amplitudes. And we have some rapid flopping between the ground and the excited state. Obviously, if you choose 2 impulses, that means that the pump and probe to be identical. You can see this rapid flopping a little bit. You can enhance the rapid flopping that is going on. Okay. Moving to the second part of the talk, which is in an atom, but it's more about this kind of processes that I explained at the beginning. It's a little bit more simple, but has more in it. So, aside from the run-of-the-mill pump probe experiments, now what is in the state of the art is doing interferometric technique. No, what is in the new kit in the on town is using interferometric techniques. So why interferometric? Because you can use the interference between different quantum paths and measure not only the ionization amplitudes, but also the phases of the scattered electron. Why the phases are so important? Because if you have obviously the amplitude and you have the phase of a function, you can completely reconstruct the electronic wave packet. And this has been a goal for a long time in science. No? Okay. You have a very popular techniques, which are the streaking, using a single attosecond pulse plus an infrared. You also have the rabbit, which instead of a single attosecond pulses uses a train of attosecond pulses plus an infrared pulse. But you have also the omega to omega technique, which has been recently used in free electron laser measurements. Okay. So we're going to go with the 2 omega to omega technique. So in this case, for instance, for argon or any atomic species that has a singlet S as a ground state, what's happening is that you use 2 ultraviolet pulses with the CEP, so with the relative optical phase between them. And what you do is by changing the optical phase between them, you can actually measure the phase difference between the different quantum paths. So I'm going to explain a little bit better. So you have the 2 omega photon, which is a single photon absorption that will leave you from the single S to a single P. Then you have the 2 omega, which is the 2 photon absorptions that will leave you, the first photon will leave you to a single P, as it did here. But with the second, you can reach the same energy, but with different symmetries and different parity. A state of different symmetry, different parity. In this case, will be a single D Eden and a single S even, while with the first photon you get a single P odd. So all of these three channels will interfere, and the idea is to change the relative phase between these two pulses and measure somehow, some way this interferes, no? That the phase difference that the wave packet accumulates in these two quantum bands. This was actually measured in neon atoms by all these guys here, and I'm gonna tell you, and you're gonna believe me, that if you use second order perturbation theory, you can actually prove that the angular distributions of the photoelectron behaves like this, with the cosine of the relative phase between the two pulses, plus a phase, which is the phase difference between the two quantum paths. Okay, so they measure in neon the angular distributions, and the idea was to fit it to this expression, which again is easy to prove that it will behave like this. And from that you can get the phase difference between the two quantum paths. Okay. So we're gonna do the same in argon. Argon is a little bit more complicated, and I think a little bit more interesting, because the two first or the second ionization threshold, so the first excited state of the cation, lies just below 2 times the energy of the first of the ground state of the cation. So what does it mean? That you can actually see, if you play well your cards, you can actually see all of the Rydberg states, or up to ionizing Rydberg states, converging to the second state of the cation, but also the Rydberg states converging to the first state of the cation, so which are below the ionization threshold. Okay, so if you do some static calculation, you see there are plenty of Rydberg states, and we wanna see how these Rydberg states affect the phases of the scattering function. Again, we can use time-dependent second-order perturbation theory for each of the paths, so you can calculate it separately. One first-order perturbation, second-order for the omega and 2 omega. If you use Gaussian pulses, then this becomes a not so hard task to do, because you can do it almost analytically. And other aspect to have to take into account is that since this is a second-order process, the omega, so you have to absorb 2 photons, that if you want them to compete the 2 different quantum paths, even though the interference should be visible anyway, you should crank a little bit the intensity that you are using for the omega. Okay. So we can use quantum chemistry for everything that is below the ionization threshold, and some more methods for the ionization amplitudes. So since this technique, the omega to omega, what we're gonna do is to prove the interference between these 2 quantum paths. It's just natural that we look at the quantum paths separately to see what we can expect. No. So we did that. This is the 1 photon cross section, so 2 omega. Ionization in the upper panel is the cross section, and the beta 2 parameter in the lower panel. No? So the green curve is barely visible, but these open circles are synchrotron radiation experiments, which are lines just above our beta 2 parameter. So we got a very good description of the process. We noticed that this spectrum, or this cross section, is dominated by some features that we can identify as the NP series, NP series of Rydberg states converting to second state of the cation. No? So the first peak will be the 4p, then you have the 5p, 6p, so on and so forth. Okay. Other interesting aspect that we can look at this is that kind of obvious that the S channel dominates at the bottom of each Fano profile, no? And we can say that because the beta 2 parameter almost go to 0 So you have like an isotropic emission that will mean that S channel is dominating. And so, like I said, so NP of the national Ripper states and the S channel dominant of resonance, and of resonance the P channel. So we can do the same for the 2 photon, so for the omega pathway. So we did that. This is the total ionization G, and the lower panels are the beta 2 and beta 4. Again, we see a collection of structures that we can identify to other series of Ripper states, but this time of different symmetry. That will be the 4S. The NS and ND series. So the first peak will be the 4S. Then you have 5S and 3D, which are pretty close together. It's always very hard to identify which peak is which. You have the next one, 6S, 4D, so on and so forth. And you also have this broad peak over here that we can identify as the 4S single P Ripper state, which is below the ionization threshold that you can access with the first omega photon. Okay, so now we put together the 2 paths and we look at the total probability. So no interference here, it's just the incoherent superposition of the 2 quantum paths, the sum to square. And this is the total ionization probability, no? So again, you have the plethora of peaks now because you have the 2 paths together. All of the Ripper states appear in each path are going to appear here. So you have the 4S bound state, and then you have the 4S single S, 5S, and the MP series, no? One thing to notice here is that for almost every frequency for emission of photon energy, there is always a single channel dominating. So most of the time is the P channel, the D. So most of the time is the D channel, while a resonance is mainly the P, and we're gonna see why this is important. Second. Okay, so now if you want to plot, if you want to look at the interference, you have to look at something angular dependent, no? And one magnitude that usually is used to quantify interference is the symmetry parameter, no? Of the photoelectrons. So what does it mean is that we're going to measure the photoelectrons being emitted at 0 degrees and with respect to the ones emitted at 180. So if you do that as a function of the frequency and the CP, now we're changing the CP between the 2 courses. The one thing to notice is that for each frequency, the asymmetry parameter is changing sinusoidally with the CP. So that means that in that way, we can control where the photoelectron is being emitted preferentially, either at 0 or 180. That doesn't mean that the electron is only emitted in that direction, but this where is emitted preferentially at 0, 180 degrees. So we can control that. And we also see that there are a bunch of structure where the asymmetry parameter get distorted. And we think that this is coming from the Ripper status that we looked before. Okay. Okay, so we can control the photoelectron angular distributions, and the symmetry changes abruptly every time that the photon energy crosses a resonance. What we can do to kind of prove that this is the effect of the world's Ripper states is just to plot the beta parameters. So now we have a beta 1, beta 3, beta 2, and beta 4 because I didn't mention, but the interference between the state of different parity is breaking the symmetry of the angular distribution. So that way you have beta 1 and beta 3. This is a little bit technical, but believe me on this. So, and the beta 2 and beta 4, which are, you can prove they are CP independent, no? So we take a line and we plot it. And as expected, what you can see, all of the possible series of Ripper states change the beta parameters change drastically when the photon energy change the Ripper state. So that was what we were expecting, no? What you can do, just to be completely sure, is to plot the angular distribution for different photon energies. So in this case, I plotted from 11 to 13 Ds as a function of the CP and the photon ejection angle. Again, this is pretty symmetric. This is pretty symmetric now. It oscillates sinusoidally with the CP. It doesn't matter the frequency of the photon energy. But since we're plotting in this region, which is just enclosing the forest Ripper state, you can see how it drastically changes in just 2 EVs, which was expected from the beta parameters that we got in the previous slide. No? Okay, back to the phases. So as I explained at the beginning, I don't know if you remember, the thing is that the angular distribution changes sinusoidally with the CP, and from that you can get the phase difference between the quantum paths. So basically what you do is select a photon emission angle, it's the line here, collect all the data as a function of the CP and feed it to this expression, and from that you get the early difference. No? So we did that. This is what we get for the phase difference for different photon angles of the ejected photoelectron. Okay, so we did that, and one thing to notice is that whenever it crosses the Ripper state, the phase changes there drastically, which is what is causing the angular distribution in terms to change drastically. And some of the times the change is a pi jump, which is pretty big or to be expected. And other thing important to notice is that okay, of resonance it doesn't change too much. You see that it's very smooth, but it doesn't change either with the angle of the ejected photoelectron. And this was kind of unexpected for us, no? And the reason why this is happening is because, as I showed before, there is always a single channel dominating at each frequency, and what that happens, you cannot expect a big difference for the emission angle with the emission angle. Okay, so we have the same Söder variations at resonance. We have a smooth behavior of resonance, and there is a small dependence with the projection. From this, so the photoelectron angle distributions and the phases exhibit the complex behavior with the photon energy. So because of the Ripper state, so that means we always use to have correlated method to do that. We have a weak dependence on the phase with the photon emission angle. This technique is very complementary to rabbit and streaking, and the next goal for us is to study using this inner shell photoionization. Okay. With that, I want to thank the people involved and thank you for your attention.
Okay, any question? Okay, I will start with one question. Okay. This Robbie flopping that you show, if I understood correct, you were explaining as you were talking about dumping, probe dumping of population. But you are using a probe of 200 nanometers. When you say dumping, you mean dumping to the ground state?
Yeah.
So that's a stimulated emission.
Yeah.
Has anyone done experiments to detect this Raleigh propagating emission?
Yeah, but they usually, I've seen experiment doing this, but they usually use the attosecond transient absorption in the group of Stephen Lehman. So, and they usually, so they have several papers publishing this, they measure the coherences on the ground state. So this has been seen before.
Okay. Yes.
Yes, I just to know the background. The oxide, actually, the ground state. You have simulated the dioxide one ground state. With tablet. When you the pump, the probe you follow the evolution of the paper. In attoseconds, the uncertainty of the energy is so large that you are starting a bunch of ground states.
Yeah,
So taking into account that bunch.
so usually you assume that this kind of calculations, 100% of the so all the population is located at the vibrational ground state because these experiments are performed usually the cold experiments are performed usually at very low temperature. We're talking about that. Correct me if I'm wrong. So it's like 20 kelvins or something. 80 kelvins, sorry, or something like this. So the molecules are very cold. But in the paper that we published with this, we have another set of calculations starting at B equal 1, so the first site at the state of the molecule, and it doesn't change too much the picture. So I think if we include a manifold of vibrational state, we're going to have some kind of average, but the same methods.
I was wondering also, can you estimate the ionization given the adiabatic before you have wave packet motion? Something that you can include in your calculations, or
so the way that you include so there are two ways. This is very useful. So there are two ways to include non-adiabatic dynamics in your calculation. One thing that you can do, and it's the most finding to be easier, is to diabatize first using quantum chemistry. And you get already your potential curves in the diabatic representation, obviously with the couplings that have between them. And then you run the time dependent exposure equation using those couplings. So in that way, I don't think so. You can do a static approximation of how the ionization will look like, but I think you have in that case you will have to solve the time dependent with those couplings inside to actually get the correct answer. There are other ways you can do it like this in the adiabatic representation and put the derivative of the coupling and stuff, but this is a little bit more complicated. But again, you will need to solve the time dependent.
questions? People is asking for a coffee break.
Yeah.